Okay, so we just saw that you can actually implement this with time of prime, but it is a little tedious and not that efficient in practice. So what we're going to see now is another hash function. It might not be as well known as this with time of prime, but it's very, very easy to implement. It's really exploiting things that are fast on real hardware. Okay? And this one is actually not going to show that it is universal like in time of prime. It's going to be too approximate universal. We're going to have a little bit weaker guarantees. So, so let's have a look here. So we're going to call it by shift. So here we are always, for this hash function, it only works or makes sense if you're hashing from a universe U. We're going to assume that this universe is always W bit numbers, unsigned integers. And we're always going to hash, oops, H is going to go from U to BL. So it's always going to output L bit hash values. Okay? It only makes sense from hashing from power to power 2, which is basically typically what you would like in most programming languages. It's convenient enough for implementing lots of stuff. So how is it chosen? So the way this hash function works is you're gonna pick a uniform random odd number A in this range to the W. This is your random seed. You're going to pick one random number. It's going to be odd. And then your hash function now is just, it looks complicated when you write it like this. So the hash function applied to an X, that's up here, it's going to look like this. So we're going to take A and multiply it with X, similar to the previous hash function. And now we're going to do modulo W. And we're going to take that number and divide it by 2 to the W minus L. I'm going to round it down. Doesn't look simpler than before, but let's try and see why this is convenient. So let's look again at this example that we're also looking at where you're hashing, say, 64-bit numbers. Say W is 64. So what is the convenient part? So let's say I'm using a programming language like C++, and I have an unsigned integer type. I think Java doesn't, but many programming languages have an unsigned integer type. I need to do modulo 2 to the W on a product. Does anyone know what happened? Like how is this taken care of automatically? So A is a random number that can be up to 2 to the 64-bit long. X is an arbitrary number we're hashing, can be up to 2 to the 64 long. So this can be like 128 bits. The convenient thing is that if you have an overflow, the way overflow is implemented in your computer is that it just automatically discards all the bits that overflow, and that's the same as doing modulo 2. So the product here, the modulo happens automatically if you choose W to be 64. Just by using an unsigned int type, it's just a product. You don't have to actually code this part. And the integer division by 2 to the W minus L, so by a power of 2, we saw that just before also, that's just a shifting of your bit pattern. So this gives this super short code. If you want to implement this, let's actually write it how you could do it in C. So let's say hash values with unsigned int 64 type hash, and let's just give it the arguments here. So we have A, X. I guess we also have L. Maybe it's not 64-bit too. What does the code look like? It's super short, and this is actually real, like only code you would have to write. Turn this, shifted, But that's a full implementation. So you can see this is much more convenient than this other implementation with multiply by prime, where you need to do 6 long multiplications. You need to manually use these Mersenne primes to handle the modulo. Here, a times x, since the 64-bit numbers, the overflow automatically takes care of doing modulo to the 64. And then you're just shifting it 64 minus L positions to handle this division by 2 to the 64 minus L. So that is the hash function, this multiply shift hash function. This is super fast in practice. And now we're going to try and show that this hash function is what we call 2 approximately universal. So for any 2 distinct keys, x not equal to y, the probability or the random choice of A here, the chance of the hash is the same as at most is 2 over 2 to the L. So maybe let's try to understand maybe one way of visualizing what is actually happening here. This a times x shifted 64 minus L position. So really what we're doing is if we look at a times x, the number, and it is at most 128 bits in this example here. But basically what we're doing is we're saying here if this is bit number w minus 1, this is bit number 0, and these are more significant bits, then the modulo is basically discarding all of this, and the shifting by 64 minus L positions is saying, let's use those L bits that are sitting here. Right, that is actually your hash value, those L bits. So that is how it works. So you're discarding these bits, you're discarding these bits, you're taking those L bits that are sitting there. That is what the hash functions actually do. So we want to analyze now, we have 2, an x and a y that are not the same. We want to argue the chance of collision is small, or the random choice of an odd A. And to analyze this, we need one fact, number theoretic fact. And then this is saying, for all, try like this, odd set, and so any power of 2, odd set in here, and for all, say, alpha, and in, let's write 2 plus, so not 0. We still have something similar that set times alpha is not congruent to 0 mod 2 to the cube. So it's something with the powers of 2 being relatively prime to odd numbers. That's the fact about these numbers. So basically, if I have an odd number, I cannot multiply with something non-zero and get 0 when I'm doing modulo 2. That's it. That's the property we need. So let's try and say, so we have this, we have an x and we have a y that are not the same. We have an x and a y. X not equal to y. And let's assume without loss of generality that y is larger than x. Let's see, when could it be the case that these two the hash of x and the hash of y are the same? So let's try and see. So what we're doing is we're doing this a times x, and then we're kind of extracting those bits there, these L bits. So we can try to look at a times x, and let's try to write an a times y. What do we have? So let's write a times y. Let's try to rewrite it a little bit. So let's try to write it as a times x plus a times y minus x. This is just a rewriting. So, and this is a times y, right? And here we're extracting L bits of a times y, and the other one we're extracting L bits of a times x. So when could these two be the same? So basically we have this a times x, right? And a times y is similar. A times y is also like this. We're also extracting these bits in here. So when could this chunk of bits be the same? This rewriting is convenient, right? Because now we have a times y is equal to a times x. So kind of you can imagine kind of process of computing a times y. We first have a times x, and then we add something to it. We have a times x already. We're looking at these bits. Now we're adding a times the difference. And we want to know whether these bits remain the same. Right, so we're adding a number, we're adding this number here to a times x, and we want to know whether these bits here in the middle stay the same. How could they stay the same? Well, intuitively they could stay the same if this number here is a times y minus x. So it's going to be added to this number, and kind of what are the only ways this can be the same? So if this number here, this a times y minus x, could be that it's all zeros in this middle chunk, and there's no carry from below. And then intuitively they could stay the same, these bits, right? When I'm adding this number to a times x, there's no carry from, if there's no carry from down here, I have all zeros, then these bits stay the same. Add them up. Does that make sense? How you're adding numbers to this. And the other option is there is a carry from below, and I am all ones, then the bits can also stay the same. And these are the only two ways these bits can stay the same. Does that make sense? So what we would kind of like to argue now, the basic idea of our proof is to show that it's very unlikely that we get one of those two. Intuitively, we're going to use almost like a union bound. So these are L bits, these bits here in the middle. If these bits were uniform random, the chance if you got this bit pattern is 1 over 2 to the L. The chance you got that bit pattern is 1 over 2 to the L. The union bound says the chance you get any one of them is at most 2 over 2 to the L. But that is the same as being C approximate universal, right? Because then with a C equals to 2, the output range is 2 to the L large, and the collision probability is most 2 over 2 to the L. And that's kind of like what we want to try and argue, that in some sense these bits here in this number are uniform random, and we only get this kind of collision if we get all zeros or all ones. That's not the full truth, but that's the intuition to have in mind for how we're going to prove it. So let's try and understand what do these bits look like in this a times y minus x. Let's try and have a look at that and see if we can analyze it. So let's introduce some notation that's convenient. So a is a random odd number, right? Which means I can also write a as 1 plus 2 times b, where b is uniform to the w minus 1. Make sense? This is the way a looks like. Let's also look at what does y minus x look like? Because this is the one we're trying to understand what is happening when we're looking at this y minus x, and we're looking at those L bits of y minus product a times y minus x. So let's have a look at let's also write it differently. So let's write y minus x. Let us write it as z times e to the I for odd z. So what do I mean by this? So what I mean here is that I can look at this difference, right? It has some bit pattern. Okay. This number can also be written as, let's take the least significant one, and let's have a number here. This is z, this is odd because the least bit is 1, and then it's multiplied with, in this case, 2 here, right? 2 to the 2. To shift it that way, right? So this is just saying I can write any number as an odd number times the power of 2. So this power of 2 is the least significant position of the 1. So let's write y minus x like that. So now with these rewritings, we want to understand what is this a y minus x, how does it look like in these bits, in these L bits there. So let's see, a times y minus x. I write it out with these new definitions. Yeah. And then I'm going to just multiply it in. So we have a z times 2 to the I plus a b times z times 2 to the I plus 1. Make sense? Just write it out. So this is what this number is. It's the sum of two things. So let's try and see what happens when we add them up. So let's first have this. This is let's try and look at the bit patterns of these two things. Z times 2 to the I. Like this position I is 1. The zeros here, and then there's something up here. The something is fixed. It depends just on what x is. Y and x are. Sorry, it doesn't depend on the randomness. So it looks like this. And then we're adding it. This b times z times 2 to the I plus 1. So what does this number look like? So it definitely, there's zeros all the way down here, right? Because it's a multiple of 2 to the I plus 1. There's going to be zeros all the way up here. And then here, there's going to be something that we don't know yet, but this is what we want to analyze. We want to analyze what do the bits look like up here. And here we have this random b. Z is not random, it depends only on y and x, the ones we're hashing. B is random, so there's something that's going to happen in these bits here. Oh. And now we're going to add these two numbers, right? We're adding these two up, which means that the result is definitely going to have a 1 in position I, and it's going to have zeros for it, and then something is going to happen here. Depends on this length. Does that make sense? Okay. Good. One more thing is this position I, since it's y minus x, both these numbers are less than 2 to the 64. These are numbers we're hashing. So this position I does occur among the first W bits, where W is the number that we're the input domain that we're hashing. It does occur before these bits that we're discarding. Discarding everything after the first W bits. This I is somewhere in the first range here. That's important. Okay, so we want to know now, we're basically taking this number, right, and then we're adding it to A times X. So that is kind of what we want to understand why. So this is A times Y minus X. We're going to add it to A times X to get A times Y. And we want to know, do the bits in these L positions change? Right? So these from W minus 1 and these L bits down there. We want to know, do these bits change when we're doing this addition? So there are a couple of cases, right? So depending on where this I is, if this I is sitting somewhere inside this chunk of L bits that we are the ones that we care about in our hash value, what can we say about the collision probability if the I is sitting somewhere in here? What can we say? So I have my A times X. I'm adding a number here that looks like 0, 0, 0, 0, 0. There's 1, and then something we don't know yet. If this I appears in these L bits that we care about in our hash value, can we say something about the chance that we hash to the same now, that these bits remain unchanged? And so again, trying to understand, we have A times X, we're outputting these L bits. We have A times Y, we're outputting these bits. Where we're looking at it is, we're saying, well, A times Y is, I start with A times X, and then I add A times Y minus X, and I want to know, do these bits change or not? They have to stay the same to get a collision. So can they stay the same if this I is among these? No, right? Someone nodding no. Because that one bit, everything before it stays the same, so there's not going to be a carry that comes from below to help us. We're going to add that one bit to some bit here, it's going to flip. So we're going to get something different. So there's no collision if this I is in among these L bits. Then there's not going to be a collision at all. So the only case we have to care about is really that I sits somewhere before these L bits that we extracted. So now we have to understand what will these bits look like, these ones that we're adding. Right? We already said up to position I, it's going to be 0, 0, 0, 0, 1, and then some. What are these bits afterwards? In particular, in this number here, this number here is B times Z. How does B times Z look like? What happens when we multiply B with Z? So here the observation is that Z is odd. That's an odd number. Okay. We have this observation here for all odd Z. For all non-zero alpha, the product is not congruent to 0 mod 2 to the Q. B is a uniform random number in 2 to the W minus 1. So let's try to look at these, the first W minus 1 bits here after this position I. How do they look like? So basically the claim is that we again have this bijection, really. So when one set is fixed, we have a bijection when we're choosing our B at random, right? So what I'm claiming is kind of like for that, how can I say, B times Z mod 2 to the W minus 1 is how do I write it? It's not congruent to B prime Z mod 2 to the W minus 1 for B prime not equal to something like this. Makes sense? Why? Maybe the easy way to say, let's say I had two where they were equal, B and a B prime, where this is equal. Then I can subtract off these two inequalities. And then I get that B minus B prime times Z has to be congruent to 0 mod 2 to the W minus 1. That would be a conclusion from B and B prime having the same value of this here. Right? Then I just subtract these two inequalities up. We get this. And now I can use my fact, right? Because Z is odd. If B and B prime, they have to be, this difference has to be 0 now, they have to be the same. So which means now that there's this bijection between the random choice of B and the value of B times Z mod 2 to the W minus 1. So there's a bijection between B and B times Z mod W minus 1. But since we choose B uniformly at random, it also means that B times Z mod 2 to the W minus 1 is uniform random. Bijection. Which means these W minus 1 bits are uniform random. I add them to something fixed, which means the defined bit pattern is going to be uniform random. I think this you can convince yourself of. If I add a number that's fixed to a uniform random number, I do this mod 2 to the W minus 1, I get a uniform random number again. So, which is the nice part, right? Because now all these, at least the next W minus 1 bits, and that extends beyond this place where we're propping the bits, all these bits are now uniform random. Which means we can now argue what we said earlier was the only way we could get a hash collision is if these bits in A times Y minus X are either equal to 0 or 0. This is the only way we could get the collision. Either a carry and all ones, a carry from below, some carry that comes from down here and all ones, or no carry and all zeros. So we can just do a union bound and ignore whether there's a carry or not. Just look at those bits and say, well, what's the probability that it's either all zeros or all ones? That probability is at most 2 over 2 to the L, because the uniform random bits, the two possible values that can cause a collision. And so the collision probability is at most 2 over 2 to the L. Probability that hash A of X is A of Y over the random choice A over 2 to the L. Which means this is a true approximate universal hash function. And I think the beautiful part is that you can write it in this super short code down here, right? It's more tedious to analyze, but this is really, really practical. Much easier than the multiply mod prime to implement.